So let's talk today about some engineering. Motion on a curve. Okay. Is that the front page? Is that what you guys have?
Yep.
Yeah, it is. Okay. I always get a little confused with this segment here. The net force on a car traveling around a curve is the centripetal force, Fc, or mv squared over r, directed toward the center of the curve. And for a level curve, the centripetal force will be supplied by the frictional force between tires and the roadway. So as you go around the corner out here, river and or mountain and first, I guess, the highway, right? As you make that turn, it's friction that actually pushes you towards the center of your curve. But if you're going really fast, then friction might not be enough. And that's why when you see, down in the States, the big NASCAR races, right? They have the track banked, right? So they can go around that corner faster. Nick, you're going to take that tube off, right? Please. A bank curve can supply the centripetal force by the normal force and the weight without relying on friction. So first of all, we're going to look at level curves, okay? So here I have a couple pictures. Here's sort of the top-down view, and here you can see the frictional force, and I'm not sure why there's two of them, towards the center, and the car is traveling forward like this. Maybe two sets of tires, yeah. No, they don't. No, if the tire actually bends like that, right? Yeah. Here we have the normal force, and we have the weight force here, and we have the centripetal force again supplied by friction. So here is an example. What must be the coefficient of friction between the tires and the level roadway to allow a car to make a curve of radius 350 meters at a speed of only 80 kilometers an hour? Now, for a level curve, the force of friction is the only horizontal force on the car and provides the centripetal force. This can be seen from the free body diagram. Now, do you guys have space? No, you don't have this example right here, do you? I always get, every year I say, I got to get this fixed. And I never do have time. Do you have that example?
It's right there.
Oh, you do? Okay, good. Okay, flip the page. Here we go. Okay, so the net force must be horizontal, pointing toward the center of the circle, and only the friction force is available to provide it. The normal force and the weight simply cancel each other out. The calculations are easy if the speed is expressed in meters per second, so here's a little review about how to do that. And you guys have all this done, don't you? Holy, easy. 80 kilometers an hour divided by 3.6, so the velocity of the car is 22. Now we can calculate the necessary centripetal force. So I guess I actually have to write it out. mv squared over r. Now we haven't talked about the mass of the car here, have we? Well, so what I'm going to do is I'm just going to use the letter m in there because I don't know it yet. 22.2 squared. The radius is 350. So the centripetal force is 1.41 m. What does that mean? No, it's not meters. It's 1.41 times the mass of the car. 1.41 masses of the car. That is our centripetal force that's required. And our normal force is mass times gravity. And again, we don't know the mass, so the normal force is simply going to be 9.8 m, or masses. Two. As long as you understand that's not meters. Right? It's at 9.8 times the mass. For this flat curve, the centripetal force is supplied by the friction force Ff. Ff is equal to mu Fn. Where does that come from? That's just mu equals Ff over Fn, right? Rearranged. And our Fn is equal to 9.8 m. And we don't even know what the frictional coefficient is. In fact, that's the question, right? What has to be the frictional coefficient? So the frictional force is going to be mu times 9.8 m. I got two unknowns in here. This sucks. But this Ff is equal to the centripetal force, which we figured out to be 1.41 m. And guess what happens? And our mu value is going to be 1.41 divided by 9.8, which is 0.141, and there is no unit on the mu. This is the minimum coefficient. Right? Any coefficient of friction greater than 0.14 will keep the car from slipping. This is the minimum value for mu. Is that a low value for mu? Yeah, remember when we did the wood on wood, we got like 0.25, I think, right? So wood on wood is not exactly rough, is it? Right? So rubber on a road, clearly more than 0.14. Is it a good thing that the mass doesn't matter? Rubber on ice might be, right? It is a good thing because the mass of the car, we sure don't want to, like if you're driving a bigger car, you want it to be able to make the curve the same as the little car, right? Okay, so interestingly enough, the mass of the car doesn't matter. Notice that the force of friction is perpendicular to the velocity, but is still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from the center to the right in this diagram if it encounters a patch of low friction like ice or oil, like Carter says. Therefore, the friction force is directed toward the center. Notice, too, that we are in fact dealing with static friction. The piece of the tire in contact with the road is momentarily at rest with respect to the road. The force of static friction is somewhat greater than the force provided by kinetic friction if the tires start to skid. So, in fact, once you start to skid, it's harder to stop skidding because you're now sliding. Yeah? Okay, so that's sort of kind of how you do it. Let's do an actual example question, shall we? No, you won't. Let me show you how actually to do it, right? That was sort of the theory behind it. You know when you're driving through the park and there's a couple places there, like the speed limit is 80, right? But there's a couple places where it drops to 70. Okay? It's a sharp corner, right? There's places, when you're going around towards Neepawa and McCreary there, they recommend 90 kilometers an hour right at McCreary, right? They recommend 9. Okay, so they're doing actual calculations that are generally based on the radius of the curve. Years ago, those of you that have ever driven to St. Rose, if you've driven to Oka River, right? Right at the golf course there, that road used to be a whole lot closer to the lake. In fact, the road is still there. That's the old highway. Okay. Now it's much more of a gentle curve, but it used to be like right along the edge of the lake and then like that, really quick, right? And it was dangerous. Like you had to slow down because of the curve, right? So they took some land away from whoever owns that land, and they actually sort of smoothed it out so that it's more of a gentle radius. It's not quite as sharp. There's another, right at the St. Rose corner there, right at the highway, you know, if you stop and you look, the highway is actually banked. Because they know that people right there aren't going to slow down, right? So they'd actually bank that highway so that you can drive your 100 at that corner. Yeah. I have a friend that he's an engineer, and I was talking to him once, right while we were doing this in class. Like I just taught this, and then I was talking to him. It was probably in the summer, I don't remember. But he says, "Oh, I got a document I can send you." So he sent me this like 45-page document that the Manitoba government puts out to their engineers about how to do all this stuff. Right? I'm flipping through it, and it's obviously a lot more complicated than we've made it out to be. But this is stuff that actual road engineers worry about. I might have it somewhere. Yeah, I'd have to look for it. I haven't seen it for quite a while. Anyways, what is the maximum speed that a 1,500 kilogram car can round a level curve if the radius of the curve is 100 meters and the frictional coefficient is 0.65? Okay, well, what do we know? We know the mass, we know the R, and we know the mu is 0.65. And the main idea is that the frictional force is equal to the centripetal force. That's the main idea. What can I find? Can I find frictional force? Well, mu is FF over Fn. FF equals FC. Here? I'm just rewriting stuff we got in the question there. So the normal force, Hannah, put it away. Now let's talk about bank curves. Bank curves are more challenging. But don't worry, I'm going to, as always, go through the theory and then make it simple for you. Civil engineers generally bank curves on roads in such a manner that going around the curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round the curve. Suppose that the radius of curvature of a given curve is 60 meters and that the recommended speed is only 40. At what angle theta should the curve be banked? Okay, so here is the thinking. You guys have this? You probably have to go forward, right? I think the bank curve example is there at the bottom. You have to flip forward for the theory, and then we're going to go back for the example, just to save a piece of paper. Okay, so answer. Consider a car mass, and I always have to have my notes here for this one because I always mess this up. Consider a car mass m going around a curve. The car's weight mg acts vertically downward. That is this right here, right? The road exerts an upward normal force F on the car. The vertical component of the reaction must balance the downward weight of the car. So F cos theta is equal to mg. So if you take this diagram right here, right? Here's the, there's the ramp there, right? This is mg right here. So if I take this triangle right there, this value right here, this is F cos theta, and it must equal mg. This mg, this bit down here, has to balance by that one, right? Are we good with that? And this is F normal. Okay? And we know that this angle here is equivalent to that angle there, right? So this is really Fn cos theta. So the vertical component of the reaction must balance the downward weight of the car. So F cos theta is equal to mg. The horizontal component of the reaction, that's this guy here, acts towards the center of the curvature of the road. This component provides the force toward the center of the curvature, which the car experiences as it rounds the curve. So in other words, and you have a blank there, I think, don't you? Oh, yeah, I gotta get this one. Okay, here we go. So you should have, in other words, you should see here, F sine theta is equal to mv squared over r. Okay? So this component of the normal force, F sine theta, has to provide the centripetal force, which is mv squared over r. Do you get a feeling there's going to be some canceling happening here?
Yes.
Okay. Now, here it says, since from the diagram. Now, here's where it always gets complicated. Look at this one here. Opposite, adjacent, right? So I'm going to write, and you should write small. I'm probably not going to have room in my space here. Tan theta, opposite over adjacent, is equal to F sine theta all over F cos theta. And those of you that have taken pre-calc might remember some trig identities. You guys do trig identities? You know, tan theta is equal to sine theta over cos theta. Remember that one? Isn't that like the first one? Go, it's grade 10? Okay. Okay, then I'm going to rewrite that to, F sine theta. I'm going to move this F cos theta up to there and flip it around to the other side of the equal sign. I'm going to write F sine theta is equal to F cos theta tan theta. I'm taking this bottom times that one. Okay, but this guy here is equal to mg, right? And F sine theta goes there, right? So I'm going to write over here mv squared over r. And here I'm going to write mg, back to black, tan theta. And what do you know? Cancel out the m's. We're going to take the g to the other side, and you're going to get tan theta is going to equal v squared over r times g. That's the formula for a bank curve. Yeah.
Oh, okay.
So this is just another form of derivation. Does that formula look kind of familiar? Go back to yesterday's flying pig. Flip through yesterday's flying pig, and what do you see? I think you should see it. Okay? Because it's all about that angle, right? Like, I'm not going to go into the whole thing, but if you look at it, you'll see that it's very much related. Note that if the car attempts to round the curve at the wrong speed, then, and the difference has to be made up by a sideways friction force exerted by the car's tire on the road surface. Unfortunately, this does not always work, especially if the road surface is wet. There's something missing there, right? Yeah. There's something missing here in this van. mv squared over r is not equal to mg tan theta. All right? Ready for the example? Because now that I've done the form of derivation, it's not actually that hard at all, is it? A race car travels along a bank curve at a speed of 120. It doesn't depend on the force of friction to keep it on the track. If the turn is banked at an angle of 25, what is the radius of rotation? So a race car designer, like a track designer, would have to know this: how fast are the cars going to be driving, right? How much banking do I need, depending on this radius, or if I can only bank in this maximum? Because eventually, if you bank it so high, the car is going to actually do what? Slide down, right? Like, you ever see those the bike racers there at the Olympics from the velodromes? You ever see how like banked those corners are? They're crazy banked, right? If that bike stopped right there, what would happen? It would just slide right down, right? So they have to actually be moving to have that inertia. Anyways, so it was tan theta is equal to, what was it? I always forget this one. This is the one I don't use very often. V squared over Rg. V squared over Rg. Oh, but I should probably do what? And they've done it already for you. Have you got that? Yeah, so they've done the divide by 3.6 for you, I guess. So that's going to be tan 25 is equal to 33.3 squared all over r times 9.8. Can you solve that? Yeah. R equals, R goes up, tan 25 comes down. So that's going to be 9.8 tan 25. You might want to use brackets on your calculator when you do that. Yeah. Oh, yeah. All you're doing is you're multiplying both sides by r, right? And then dividing by tan 25. What do you get? I get 243. Okay.
43 meters.
So, you know, in reality, I made it pretty simple for you, didn't I? Once you do the form of derivation. Okay, so there are, at the back there's 6 unbanked curve questions. There's a few banked ones. Questions number 7 and 8 are bonus. They are extremely challenging. I've never had anyone solve them, including myself.
What? And why are we?
I'm waiting for that genius to show me how to do them. I got 7 more years.
Tired?
Yeah.
Maybe the only be a substitute got this.
I could, but then I won't care so much. Not about that question. I'll still care. Yeah.
How do you not have the answers for that? Well, the answers are there.
Yeah, I got this out of a book, but I cannot solve those myself.
You can get answers the wrong when you were right.
Well, maybe,
It's always that way.
but I have not been. Now, the problem with 7 and 8 is, up to number 6, they're always just like a frictionless. You know, this would actually work. I should explain this. I didn't really explain this. This would work if this was like a frictionless surface. Like, this could be completely ice-coated, and that car would still be able to make that corner at 120 kilometers an hour because of the bank. There is no friction at all here. It's entirely the normal force, the component of gravity that's causing us to go around like that, right? Now, generally, people don't round corners where there's no friction at all, right? So that's the other thing the engineers need to work into this is, there's going to be some friction, right? So they can count out. However, here in Canada, do you think that they count on friction a little bit? I mean, it would probably be a cost thing, right? Because it would probably cost more to bank it more. I don't know. It'd be an interesting discussion with the highway engineer. Anyways, I should talk to Josh to see what he says. So up to number 6, they are frictionless. They're number 5 and 6. Those are not cars. Those are actually planes, but the same principle is true for the lift force. So you can try those. But again, don't freak out if you can't do 7 and 8. They are extremely challenging. I also have a pre-test that doesn't have these on it actually. So I'm going to hand that out today, and I'll